Okay, we are back. We are looking at Chapter 8. This is Basic Statistics. We're looking at 8.3. So let's take a look. That starts on the note packet. Page 5, we already did. 6, we already did. All right, starts on page 9. So hypothesis testing, t-test for the mean. So when do you use a z-test? When do you use a t-test? You use a t if you do not have the population standard deviation. And a student asked a really good question. She had asked, well, wait, but on Excel I could do standard deviation for population instead of standard deviation for sample. Won't that give it to me? The answer is no. You only get to use that on Excel if it identifies it as a population. If it's a sample, you have to use the .s as a sample. And so if you don't have the population standard deviation, you don't have the population standard deviation. We can't use Excel to generate it. All right? So let's take a look at page 10, actually. So they have us put in a bunch of data. First, they give us the t-test. So let's take a look at that. What does that look like? T-statistic, it looks just the same. We have x bar minus mu over s divided by the square root of n. So it looks very, very, very similar to the z. It's just the cutoff point is going to be different on our graph. That's all. So t, you find t almost the exact same way that you find z. It's just your critical value on your graph of your curve is going to be different. All right, so let's take a look. On page 10 here it says either we reject the null or fail to reject the null. That's how we always roll with these. So here are 20 gas tanks filled up. I know you probably remember that from test 3, or test 2, was that test 2? I think that was at the end of test 2, sorry, the end of test 2. So different values. So you plug in those 20 values into Excel, have it find on Excel, remember the average, that would be 26.45, that's the mean. And do standdev.s. So stdev.s, that's for a sample. It's 2.874. So now, since this was just a sample given, we for sure, and you read through it, it doesn't have the standard deviation of the population. So we have to use t. Also, the number is less than 30. All right? But regardless, if you don't have the standard deviation of the population, you're using a t-score. All right, so now it's always 5 parts. A is the hypothesis. So state the hypothesis. We have the null and the alternative. The null hypothesis in this case is it equals 30. And we suspect, based on the data we gathered, it's actually less than 30. Because look, we have the mean is 26, which is less than 30. So now we're going to decide, is it significantly less than 30 or not? So this is the test. You may have also seen it in I've seen it in other books. Our book usually goes with equals and then greater than or less than. They usually don't play around with the null hypothesis with anything other than equals. So this is fine. If you wanted to say your null was the mu is greater than or equal to 30, that's fine. But this is always either greater than, less than, or not equal to. You'll never have a greater than or equal to in your alternative hypothesis. All right? So that would be okay. I'm usually going to just stick with the equals sign. So that's sort of like what they claimed you would get, your miles per gallon when you bought the car. They said it's 30, the average is 30, but your average was less than that, 26.45. So now we're testing to see, is it significantly less? Is that a significantly lower number to that? And that's where your alpha comes in. So at what percent do we decide to reject the null and conclude that we're getting less on average? So there's your standard normal curve. It's a one-tailed test, so it's just on the bottom. And so we look up our critical value, but this, we're gonna look it up on the chart as a T, not a Z. So here we go with the chart. We've got our chart. There's confidence interval, one-tail test, 5%, and now we go down to 19 because there are 20 pieces of data, so the degrees of freedom are 120 minus 1. So that is, what is that? 19, 1.729 is what I'm going to use. 1.729. All right? Okay, oh, and it is on the low end, so it's actually negative 1.729. Don't forget the little negative in there. I probably wouldn't take that off on a test. I'd probably just put the little negative in there for you. But you really should have it as a, anything lower than 0 on the normal curve is negative, above 0 is positive. All right, so now, C. We'll find our test statistics. So it's always hypothesis, curve, draw a curve. I want a curve for every round. So these 5 steps are going to be laid out on this last test. Do A, B, C, D, E, A, B, C, D, E. So A, B, so always state your hypothesis. Draw your curve marked with the critical value. The shaded area means we reject the null. The unshaded area means we fail to reject the null. So we find our T statistic now. That's 26.45 minus 30 over 2.874 divided by the square root of 20. And so now we got negative 3.55 on the top. On the bottom, when you divide that out, you take that divided by the square root of 20, you get 0.64264, I think it's 5, blah, blah, blah. I'm gonna round here, go 6. You could probably go 3 or 4 places and that would be fine after the decimal. I'm going 6, it looks like. All right, so we divide it, we get negative 5.524. Is that in the shaded area or in the non-shaded area? So now we go back up to our picture. We take this and we graph it onto our picture. Well, yeah, that's way in the shaded area. If this is negative 1.8, that's negative 5.5. That's way down there. So that's definitely in the shaded area. So then letter D is we either reject the null or fail to reject the null. Well, this is really heavy evidence to reject the null hypothesis. All right, so we reject the null at the 5% level. And then letter E, we state it in terms of the problem. We restate our conclusion. So this was find the test statistic. This is do your conclusion. And then letter E, we'll call that the write-up. Meaning you put it back in the context of the problem. So we reject the null, that's gone. And this is what we are concluding. We're concluding that your average miles per hour is less than 30 miles to the gallon. And so, how can we say that? The average mile is below 30 miles to the gallon is how we could say it. So we conclude the average miles per gallon is below or less than 30 miles per gallon. Based on, there's evidence to make that conclusion. All right? Excellent. So letter D on page 10 says, what is the p-value for this sample? And this is where our packets fail us. They don't have p-values for the t distribution. They have it for the z distribution, but not for the t distribution. And so that is optional. I mark that down on the notes as optional. If you have a graphing calculator, you can put it into the graphing calculator, and it'll kick out this. So I'm going to write this up for the notes, but you don't have to worry about this. This won't be on the test, or it won't be on graded homework, where they're asking you for the p-value. So what is a p-value? The p-value is this percentage, the percentile, basically, that would match with this t value, the t statistic. So what value matches with that? Well, according to the TI calculator, 4 zeros, 0.0000125. Well, how do we interpret a p-value? The p-value is stated like this. It's a little tricky. If the null hypothesis were true, if the null were true, so if this were a true statement, we would get results like this, and we'll make that into a percent. It's still not much, 0.00125% of the time. And so do you see, that is why that is really strong evidence for the alternative hypothesis. That's why this is what we made our conclusion about. Because if this were true, we would only get results like this really close to 0% of the time, 0.00125% of the time. And so let's pretend that that wasn't that. Let's pretend the t-score was something like 1.2 or something like that, where this was 80%, 83%. Well, then it would read the p-value 0.83, and we would say if the null were true, we would get results like this 83% of the time. Well, that's really good evidence for the null hypothesis. So that's why we should have things set. Your significance level should be set. So then we know if it's big or small. You know what I mean? Because that's relative. So let's pretend for a moment this came out to be 6%. What if the p-value was 6%, 0.06? Well, we set it as significant at 5. So 6% would have fallen in the unshaded area. And then we would have failed to reject and went with that. It was small, but not small enough. All right? Okay, let's look at more examples. When you look at more examples of these, I think they tend to make a little more sense as we go. All right, so page 11. Again, they talk about using the TI. Don't worry about it. If you don't have a TI, you don't need it. It's not a requirement. If you have one, that's why it's in there. So here's an example. In a study of 14 random skateboarders, the average number of times per year they were in the hospital was 3.2 days, with a standard deviation of 0.6 days. All right, so that's talking about the random sample 14. All right, test the claim that skateboarders spend an average of more than 3.5 days per year in the hospital at the 1% significance level. So they set that at 1%. All right. So let's take a look. This again is going to be T. We're We're going to use the t distribution again. And so we're going to run through those 5 steps that I just erased again. So let's do it. So the null in the alternative hypothesis, the null is mu is equal to 3.5. The alternative is mu is greater than 3.5. And again, you could have had a null be mu is less than or equal to 3.5, or mu greater than 3.5. I'm just going with equals. Your book usually uses equals, so I'm trying to keep it like the book for you. All right, so let's look at B. Well, this one, based on the information they gave us, we're worried about this at the 1% level with alpha equal to 1%. And so we again go to the t distribution, not the z, and 13 degrees of freedom, and we look that up. And so that comes out a critical value, or t-score, the cutoff t-score is our critical value, is 2.650. And then let's go ahead and find our t-statistic. Well, if you look at it, it's definitely not going to be here. It's going to be negative. So it's going to be below the 0 part. It's going to be in this half. We're going to end up in the unshaded area. Because look at what happens. We got 3.2 minus 3.5 over 0.6 divided by the square root of 14. So negative 0.3 divided by 0.160356. And negative 1.87. So that is clearly, that's almost 2 standard deviations below the mean. Definitely not above on this end. So not even close. Even if it was positive, it still would have missed it. So negative 1.87, so we're in the unshaded area. That is failed to reject the null. So that is my conclusion, is failed to reject the null. At the 1% significance level. All right, and then what does that mean in terms of E? Well, again, you could say, well, this was the conclusion we made, that it's equal to 3.5, or like I said, if you had the less than or equal to 3.5, it's not that. Lots of times you'll see write-ups, and again, I'll mirror the book this time. They'll always give it in terms of the alternative hypothesis instead of the null. So instead of saying we conclude the average stay of skateboarders is 3.5 days in the hospital per year, we just say there is not enough evidence to conclude that the average annual stay in the hospital for skateboarders is more than 3.5 days. So there's not enough evidence to conclude that it's more than 3.5 days, which is, I think, what I wrote on the notes. I said there's not enough evidence to conclude skateboarders spend more than 3.5 days in the hospital annually. That's a little better. Okay, so again, it says find the p-value for this test. You do not have to do that. That is optional. If you have a TI 83 or 84 graphing calculator, you can key in the keystrokes it tells you to put in. If you do that, the p-value would come up to be 0.9579. So again, I'm not going to write that up this time, but the p-value of that means if the null were true, we would get results like this about 96% of the time. So that's really good evidence for the null. We're saying basically if this were true, we get results like this 96% of the time. That's a lot. And they wanted a 1%, so it was nowhere near 1%. All right. Okay, let's take a look. All right, the next video we'll do will be 8.4.